Alright, so I think this is recording. Let's take a look here at this Skill 2E Day 9 homework. In problem 1, they give us two functions and they ask us a series of things finding the domain. For part A, to find the domain of f of x. Well, if you look at f of x, there's no variable in a denominator. There's no variable underneath the square root, so the domain is all real numbers. Written in interval notation, that's from negative infinity to positive infinity, and both of those are parentheses and not brackets. For the domain of g, we don't have any square roots, but we do have a variable in the denominator, so hopefully it's clear that x cannot be negative 4, because if you try to evaluate this function at negative 4, then you get 1 divided by 0, which is undefined. So negative 4 would not be related to any y value. That's why we have to throw negative 4 out of the domain. On the real number line, if you've got negative 5, negative 4, negative 3, and so on, we're excluding negative 4, but everything else, all the other real numbers are in the domain, because none of these other real numbers will cause division by 0. And we don't have any square roots, so we don't have to worry about that. Written in interval notation. The left arrow is shaded. We always read the graph from left to right. The left arrow is shaded. That's negative infinity. We exclude negative 4. Or, that's the union as that mathematical symbol, and we can translate it as the word or. You're in this interval from negative infinity to negative 4, or you're in the interval from negative 4 to positive infinity. These need to be parentheses to exclude. You wouldn't have brackets there. So there's our answer for part B. For part C, they want us to find the domain of this composition. So the composition can be thought of like an assembly line. Two things have to be true to be in the domain of this function composition. This is where the domain is, and any value, any real number that's in the domain has to make it through the function g and through the function f and produce a number that's in the range of this composition. So you have to get through each function. So for x to have an output of g, x has to be in the domain of g. Then g of x becomes the output here, but g of x is also the input for f, so it has to be in the domain of f. This little epsilon means an element of, or you can think of it as a member of, or that it belongs to that set. Well, we've said the domain of g was x not equal to negative 4. We can come back and write that in interval notation later. The domain of f was all real numbers. So we don't have any restrictions here. Anything that g produces will go through f with absolutely no problem. So the domain of this composition, the only restrictions come from this function g, because f will accept any input, any real number that you want, and f will produce an output of a real number. So the domain for this function composition happens to be the domain of g. That may not always happen in every problem, but it will happen in every problem where this domain of f is all real numbers. There's our answer for part C. In part D, they changed the order of the composition, so now elements from the domain are first going through the function f. So it has to be, two things have to be true. X has to be in the domain of f. Every input has to be in the domain of the function. Well, now f produces its output, and we use the symbol f of x to represent that output, and it has to be in the domain of g. And it we need it to produce a number in the range. If in fact the number is in the domain, it will make it through both functions and produce a number in the range. The domain of f is all real numbers, so we don't, guaranteed that we'll have an output. There's no restriction from f. However, the g of x will not like the number -4. So we need to prevent the output of f from being -4. That does not mean that we're going to throw -4 out of the domain. We never throw out this intermediate value. What we need to do is recognize f of x cannot be a -4 because g, -4 is not in the domain of g. G will not accept the -4. If it tried to accept it, it would produce 1/0, which is not a real number. Alright, so let's figure out what x produced this -4 from this function f. So f is 3x plus 5. If we allow that, if we say, hey, what value of x causes this to be -4, let's solve this equation. Let's subtract 5 from each side, divide by +3. And what this tells us is that f evaluated, the lights just went off because I'm in the corner. F evaluated at -3 is producing this -4 that we do not want. So if you input -3 here into f, you get -9 plus 5, which is a -4, and then that -4 does not make it through g. We don't throw out -3, we throw out, we don't throw out the -4, we throw out the -3 that caused that -4. So both of these have to be true at the same time. You have to have the set of all real numbers. Well, that's easy. That's just the whole number line. And x cannot equal 3. Those two things together just means that x cannot equal 3. So our domain of g composed with f is all real numbers excluding the number -3. So I often just describe it as punching a hole in the number line. All the other numbers, we will not have a problem with any other real number. So any number that we select to be the input for this composition, as long as it's not -3, it will make it through both functions and it will produce a number in the range. Alright, so I'm limited on time, so I'm just going to have to keep going. It takes time to make multiple videos and to save them and upload them. It'll take less time if this is just one large video. So if we go on now to problem number 2, we want to find the domain of f. We don't have any variables in a denominator, but we do have a radicand. This variable that's underneath the radical has to be non-negative. And if we solve this inequality, as long as x is 9 or larger, then this subtraction will be a positive number. So as long as we're equal to 9 or larger, pick any number in that shaded region and input it into this function f, the output will be a number. So the domain of f written in interval notation, we need a bracket at 9 to include 9, and it needs to be larger. If it were smaller, like 2 times 8 is 16, but 16 minus 18 is a negative number. So you can see that's why we have to shade to the right. For the domain of g, we don't have any variables in a denominator. We don't have a square root. So the domain of g is all real numbers. To find the domain of f composed with g, recognize that we start with the second function and then apply the first function. It's I think it's best thought of like an assembly line. Every input to a function has to be in the domain of that function. So x has to be in the domain of g, or otherwise it won't produce an output. The output of g, which we call g of x, is the input for f, so it has to be in the domain of f. We never exclude these intermediate values from the domain. We exclude values that produce that intermediate value. The domain of g was all real numbers, so we don't have any restrictions to begin with. So any number that we give g, it will produce an output. However, f is more picky. F wants the output of g to be bigger than or equal to 9. So what is g of x? Well, it's x squared minus 16. That has to be greater than or equal to 9. Now that's a quadratic inequality. We looked at that in skill packet 1. This is a little bit harder to solve because first you want to get it to 0. Now that's pretty common for any quadratic equation or inequality. Get it in standard form. Get it equal to get it equal to 0. So if I subtract 9 from each side, and I just change the arrow, if I change it to an equal sign, solving this equation is finding what they often call critical points. So if I factor this, I have x plus 5, x minus 5, and that equals 0. So we've seen that this will divide the number line into 3 pieces. Pieces that are to the left of negative 5, pieces that are between negative 5 and positive 5, and pieces that are larger than 5. Where did I get negative 5 and positive 5 from? They were the solutions to this equation. Because this inequality, this arrow is underlined, we will include our critical points in the domain. And so now we have to sit there and say, well, if x were, say, negative 6, I just randomly picked a number that was smaller than negative 5. Whenever possible, I'll pick 0 because it's easy to do arithmetic on. And then I'll just go ahead and pick positive 6 to be in this region C. These are representatives of each of these regions. If we come back up to, where'd it go? Well, let's write this as x squared minus 25 greater than or equal to 0. If I plug in x into this inequality, will it be a true statement or a false statement? If I square negative 6, I'll get 36. 36 minus 25 is positive. So that means I'm going to shade region A, because any test point that I would have picked and squared it, that subtraction would be positive. Plug in 0, 0 squared is 0, and 0 minus 25 is negative. I'm not going to shade in this middle region. Plug in 6, 6 squared is 36, 36 minus 25 is positive. I'm going to shade this region. So these two things have to be true at the same time. We have to be all real numbers, and this picture, real numbers that are less than or equal to negative 5 or greater than or equal to positive 5. For those two things to be intersected, you just get this same picture for the domain of this composition. So yeah, the domain then of this composition, I'm just sitting here thinking for a moment. Yeah, g of x had to be greater. I just want to make sure I didn't make a mistake with you. So from negative infinity to negative 5, union positive 5 to infinity. So there's our answer for part C. In part D, they change the order of the composition. So the domain of F, the domain of G haven't changed. And the idea that you want to make it all the way through both functions to go from a number that's in the domain to a number that's guaranteed to be in the range. So the domain of F, X has to be in the domain of F. Well, we saw that the domain of F was x greater than or equal to 9. The second thing that has to be true is the output of f, this f of x, has to be in the domain of g. Well, that's no problem, because g isn't picky at all. G is, the domain is all real numbers. It takes any number that f can produce, and it will produce a number. So as long as we start this with x greater than or equal to 9, this composition will produce a number in the range. So that's our domain for g composed with f, is from 9 to infinity. Alright, that's our final answer for part D. For part A here, this is the last problem. For the domain of f, we want this denominator to not be 0. So we want 2x minus 6 to not be 0. Well, x can't be 3 then, because 2 times 3 is 6. So that's the domain of f, is all numbers excluding the number 3. So 2, 3, 4, and so on. Of all the numbers on the number line, that's the only one that causes this problem. So we just punch a hole in this graph and exclude that value that caused division by 0. Because this denominator was pretty simple. In interval notation, the left arrow is shaded, so we have a parenthesis and negative infinity all the way up to positive 3. We exclude positive 3, so these are both parentheses. And then 3 to infinity is that second interval. This union is the idea of or. You're in this shaded region, or the number is in this shaded region. Alright, so for the domain of f, it's the same idea, but it's even simpler to solve. We can't divide by 0. We don't have any square roots in either one of these to worry about. So for the domain of g, you can see by inspection that x can't be negative 1, because we need to prevent x plus 1 that's in the denominator. We need to prevent x plus 1 from ever equaling 0. So for the domain of g, we're going to throw out the number negative 1, and on the number line we just punch a hole in that number line at negative 1, and all these other numbers are in the domain of g. So written in interval notation, we're from negative infinity, because we're reading the graph from left to right always, up to negative 1, or we're from negative 1 to positive infinity. So if we look at the composition f composed with g, we have to recognize that we're starting with the function g and then finishing with the function f. Two things have to be true to be in the domain of this composition. First, the numbers that we input into g need to be in the domain of g. And then second, the numbers that we input into f need to be in the domain of f. Well, we said that the domain of g excluded the number negative 1. Okay? And we said the domain of f excluded the number 3. Now, we don't say x can't equal 3. We say the output. We say g of x can't equal 3. So we've got to figure out what value of x produces, what value of x, if you plugged it into g, will produce a 3, and don't do that. Because we don't throw out the intermediate value. F will not accept the number 3 because the output then would be undefined. We throw out the numbers over here. So g of x is this ratio x minus 2 over x plus 1. What if that were equal to 3? This gives you the output. Well, let's cross multiply and figure out what x causes this so we can prevent it from happening. So along the yellow diagonal, we have 3 times x plus 1. Along the green diagonal, we just have x minus 2. If we distribute, we get 3x plus 3 equal to x minus 2. And if we collect the x's on the left-hand side and the numbers on the right, we get 2x is equal to -5 if I haven't made a silly mistake, or that x is half of -5. Since that's a terminating decimal, I can write this as a decimal number without, and it won't be an approximation, it'll be exact. I can write this as -2.5. So some people may prefer that. Well, what does that tell us? That tells us that if you input this -2.5 into this function g, the output will be 3. Well, so if you start here with a -2.5, g will accept that -2.5 and it will produce the number 3. And so far, no problem, because remember, we've got to make it all the way to the end. But then f sees the number 3, and f goes, no way, Jose, because you have a 3 here, but then you'd have 6 minus 6, and it can't produce a number. So f starts yelling at g, I don't know what you just gave me, but don't do that. You just gave me 3. I don't know what started this mess, but don't do that again. So g has to say, okay, I can no longer accept this number -2.5, because according to my rule, it will produce a 3, and f can't handle that. So if we want to prevent the output of g from being 3, we have to prevent the input into g from being -2.5. So there's two things that have to be true then. We can't equal -1, and we can't equal -2.5. So if we draw a number line, here's -2.5, say, we're going to exclude it, and here's -1, we're going to exclude it. But the other values are okay. These are the only values that we're excluding from the domain of this composition. So the domain of f composed with g is from -infinity to negative. I listen to the Bob and Tom show when I'm at school doing this, and they're talking about something that's kind of funny. Alright, so there's my answer for number 3, part C. Let's do the last problem here, part D. G composed with f means that we start with f and finish with g. Two things have to be true to be in the domain of a composition. X has to be in the domain of f. Every input has to be in the domain of its function. F of x is now the input for g, so it has to be, the input has to be in the domain of its function. Well, we said that f, the domain was that x can't be 3. So we know that we're going to exclude that. Now, g can't take the number -1. It just can't stand it, but we don't throw out the number -1 from the domain. We have to figure out what x produced this -1 and then throw the x out, because this is where the domain is. We do not exclude these intermediate values. We do not want f of x to ever equal -1. But in order to figure out what x causes that, we do have to temporarily let it equal -1 to solve this equation. X over 2x minus 6, that's what f is. If we write -1 as -1 over 1, that's a proportion. And you guys are very good about solving proportions. You know how to cross multiply. You do it very well. So if we multiply along this yellow diagonal, I get x. If I multiply along this green diagonal, I get -2x plus 6. If I add 2x to each side, and if I divide by 3, what does this tell me? This tells me that if we evaluate f at 2, that we get this dreaded -1. So if we allow 2 to be in the domain, f is going to produce a -1, and then g is going to say, no way, I can't handle that. Its output's going to be undefined, because when it sees this -1, it's going to produce -3 divided by 0, and that's not a number. So g yells at f, hey, don't do that to me. and F says, okay, I can no longer, I don't have a problem with the number 2, but my partner back here, if I accept this 2 in the domain, my output's going to be -1, and G can't handle that. So we look to say, well, with these two ideas going on at the same time, X can't equal 3 and X can't equal 2, and that's the domain of this composition. So if we real quick draw a number line where we've got 1, 2, 3, we're excluding the number 2 and we're excluding the number 3. Everything else is in the domain. These other values will make it through both functions. Every X will produce some number that will be in the range. It'll be related to some Y value, some output. Alright, to describe this, we read it from left to right. So the domain of this golf is from -infinity to 2, and then from 2 to 3, and then from 3 to infinity. So I hope that helps. Ask any questions as needed, and I will talk to you later. Bye.